Hello, welcome to today's webinar presenting ATENA basic tutorial, which is shear wall with round opening. You can find it in ATENA Center tutorials, and also you can check the PDF manual there. The structure consists of the wall that is enclosed between two beams. The bottom beam is the support and the top beam transfers the shear load. You can see how it is reinforced. And we can start with the opening of ATENA Preprocessor 2024. So now we can proceed to settings and project settings to change the project name from default project to shear wall with round opening. What you might have noticed is whenever I click the mouse, the left click, it shows like yellow on the screen. And we proceed with the geometry. We are first creating points. When you have that point create settings, you can jump in between with tab, and once you jump with tab to apply, you just press enter, so you don't need to use mouse at all at this point, and you are just entering the points by its coordinates. So these are the first points we are going to use for creation of the middle part of the wall. You can shift the view with holding the shift and right mouse click. And then we continue with extruding the points. For the selection of the points, you can see this square target and the view. And when you are selecting more geometry entities, you need to hold Control button on your keyboard. Otherwise, you would choose just like one geometry and would immediately skip to select the start point for extrusion. And again, you can use tab to jump in between and press enter when you want to apply it. So we continue with creating line segments directly in the view, selecting the points, and when we want to break in between selection of the points, we just press escape, and double escape is escaping completely creating the segments. So we proceed with creating the arc. We select the method start and radius. So we are selecting start and end directly in the view, and then radius we are adding in the settings. And we have to select the third point, which is called like that is the inner point of the circle, and it defines the plane where the circle lies. In following part, we create the first surface, so we can select just one curve on the boundary. It automatically shows us the rest of the boundaries. If we agree with it, just press enter, and you can see that purple line on the edges of the new surface. You can see that I'm already selecting the surface to create the first solid, that we are extruding the surface in X direction. The sky blue line indicates the first solid. Pressing the left mouse, holding the shift is turning the view. We continue with creating bottom beam. First we start with like first point. When the first point is created, we are extruding the point into the line. In X direction. Apply. After that, we extrude the line in that direction to create surface. And last step is to extrude the surface in Y direction to create actual beam. And finally we are going to copy it, so we have to uncheck extrude and check the copy. And we are copying the bottom beam to the top of the wall. So the concrete part geometry is done. And you can change the model view from wireframe to solid, or there is also transparent version. Finally, we can divide geometry into different layers. So we just rename the layer that we have there as a wall, then we create new layer, we rename it to beams, and now all geometries are in the layer wall. So we want to select like beam layer, select the solids, and then we can choose the solids which we transfer to the beam layer, and we go to layer settings to add the selected geometry into the layer, and then we can uncheck and check the visibility of the layer and see what is in which layer. Now we are going to create another layer called bars, where we place the discrete reinforcement. So we continue with making the points that are the edges of the reinforcing bars. First bars that are made are two bars going through the small pillar that is on the edge of the wall opening, and we create the bottom 2 points which are extruded towards the top of the structure. And all this discrete reinforcement is set directly in the middle of the thickness of the wall. Now those two bars are copied to the other edge of the wall. We proceed with bars that are on each side of the wall opening. First we create the points that are at the bottom beam, both of them, and then we gonna extrude those 2 points above the opening in the wall. So another bar, discrete bar that is part of the geometry, we are creating with 4 points. It will be above the wall opening. Here you can see the first point. And there is the second point. That is the part that is above the opening, and it will turn upwards towards the top beam. You can nicely see those points as they are like the preview, and when you are finished with the defining, it changes the color to blue. In the preview it's just black. And we connect those points with line segments. First just the straight ones above the opening and along those rebars that are already there. And that middle part, the turning point, will be an arch. And we change the method again to start and radius. And just make sure when you add the radius that the point that is defining is really in the middle of the wall. So the x coordinate is like in the middle of the wall, so it's not turning outside that plane. And when you check it, when you turn the view, you can see that the arches are where it should be, lying in the middle plane. So in the last part of creation of geometry, we make the reinforcement mesh that has spacing of bars 100 millimeters, and we start with bars at the bottom of the beam that are parallel to y-axis. First point we make, and that point it needs to be extruded in y direction. The whole mesh that we are creating now is again in the mid plane of the structure. And the first bar at the bottom beam that we created, we are going to copy 3 times below the first one. And sometimes other geometry is a little bit interfering, so we can switch off layers that can help us. Yeah, so now we have the first part of mesh, and we create another layer for this mesh reinforcement, which will be helpful later on for assigning of materials. So following, we are copying 1 bar above the opening, and then we create other copies with, again, spacing 7 more copies towards the top with the spacing 100 millimeters. And finally, we need to create parallel bars next to the opening that are a little bit shorter. So we just copy 2 points on the edge and we extrude them towards the opening. You can double check all the sizes and coordinates of the geometry in the PDF tutorial that I showed at the beginning. And now we proceed with the bars that are parallel to z-axis. First we create the point at the bottom beam and we can extrude it towards the top beam. Then we can copy this bar 8 times towards the opening. Again, black is showing just the preview. Once you apply it, it turns blue, the geometry. And now we're gonna copy just edge points or the bars that we have there already, because we need to make shorter bars below and above the opening. We extrude them accordingly. At the bottom beam there are shorter bars, of course. And above the opening there are bars about double of the size. And when we have these bars, we can again copy them 4 times towards the edge. Maybe I can remind that when you want to select more entities during this extrusion or copy, you have to hold shift for that. And the last part is just one more bar that is going through the pillar on the side of the opening. Well, now whole geometry is finished. You can have a look on all the layers. And we can also change the view. Maybe transparent one is better. You can see reinforcement inside the structure. And we can proceed to materials. So once the geometry is done, we can create materials that are used in the analysis. First, we start with plain concrete that will be in the part of the wall. And we generate material that is based on cylindric strength 30 megapascals. We rename the material, and then we can also adjust the material parameters. In this case, it will be Young's modulus 31.7 gigapascals. Then we change the tensile strength to 2.6 megapascals, compression strength to 37 megapascals. We change fracture energy to 130 newtons per meter, and we activate the shear factor, change it to 400. And in compression tab, we change the plastic strain to 0.0017. Onset of concrete crushing is minus 20 megapascals. And we activate the crush band, which is basically the smallest size of the structure under compression, especially when it is like the one that might fail early. And now we prepare the reinforcement material. It's represented by multilinear function. It's generated based on the yield strength, and epsilon, UK, and K parameters are basically corresponding to elongation class A in Eurocode. We name the material D6, which is like 6 millimeters diameter of the material, of the bar, I mean. The secondary bar is generated based on yield strength 480 megapascals, and epsilon and K parameters are corresponding again to the elongation class A according to Eurocode, as all the other reinforcement we are creating for this structure. The diameter is 12 millimeters. We go to create the third one that has yield strength 470 megapascals. and the diameter is 8 millimeters, 10 millimeters, sorry. The last one is actually the one with 8 millimeters, and we have the characteristic strength 420 megapascals. It pops up the question if we are sure about it. We are. So the diameter is 8 millimeters. And until now we created the plain concrete for the wall, all the reinforcements, and now we are going to create concrete that is in the beams. First we start with the base concrete, which is generated based on the strength value 80 megapascals, and this concrete we use just as a base for the reinforced concrete material with smeared reinforcement, so we name it concrete beam base, and we keep the parameters that were generated. We are not changing them. And when we want to create that material with smeared reinforcement, we have to change the prototype and go to combined material. We first rename it that it's like concrete for beams, and then we can see that there is first material for solid part, which in our case is concrete beam base with the ratio 1. We are not deducting the area of steel. We activate the material, and then we add the reinforcement with the ratio 0.0028, which corresponds to spacing 100 millimeters, and direction is Y, and we are using the bars with 6 millimeters. We use the same ratio in another direction, which is Z, so we have basically covered the plane of the wall, but we also add the third direction, which is X direction, and that basically corresponds that we have stirrups there in the beams. So once the materials are done, we need to connect those materials to the geometrical parts, and we are using this building element types. In this case, we choose beams, and geometry entity is solids, and the assigned materials for our beams is concrete beam. We assign it to the geometry, then we go to the walls and assign the material of the wall. This is actually just preparation for the BIM system, and then we can switch off the parts of the concrete parts, so we can more easily add the material to our bars. First of all, we are naming them properly, so we know which are the diameters and which materials we assign to it. Choose the perfect bond and assign it to the lines. The next one is bar with 10 millimeters diameter, so we have to change the material and also the bar diameter, that it's correct. We assign that to the geometry again. Last bar from rebars layer is the bars with 8 millimeters diameter, so we change it properly and assign it to the curved bar above the opening. And I didn't change the name, so I repair that it's bar with 8 millimeters diameter. And the last is the mesh of the reinforcement, that is with the bars 6 millimeters in diameter, so we name it again properly, that we know which material it is. After pressing OK, we can again assign it geometry, and we can have a look on all these material parts that we assigned, how they look together in the geometry. Yeah, and I actually noticed that I forgot to change the bar material, the last one, so to repair that. So now we go from input data to FE mesh generator and preview the finite element mesh, the default one, which is tetrahedral. And on the right side in FE mesh settings, you can check or uncheck the visibility of the mesh. For another settings of the mesh, we can hide the reinforcement. And we go to the type of the mesh, and we are going to change it from unstructured to structured one. In case of solids, we select the structured mesh, which is hexadominant, and assign it to the beams. And then we assign the structured mesh, which is quad dominant, to the extruded surface of the wall. And in FE mesh generator, we check how our mesh changed. So we can see that we got some hexahedrons and also some wedges in the middle. But we want to improve it more, of course. So we go to input data again, and we assign the different size. So we select like 0.1 to the beams, to the solids, and then we assign another one to solid. For the wall, we can create a little bit finer mesh, 0.03, and we can see what we get from that. And applied equidistant on the beams actually made the mesh parallel, which was not before. And we don't have still structured mesh in the wall, so we assign the extrusion there to get proper structured mesh also in the thickness of the wall. So now it's nice mesh for simulation. Then we can continue an input data with analysis. First part is load cases. In this example, we are loading with prescribed deformation. So we changed from the load case forces to prescribed deformation. And then we go to boundary conditions that are interconnected with the load cases. And first we start with supports at the surface on the bottom beam, and we have to choose the load cases support, and then we have support that is assigned in all directions, and with enter we assign it. Then we continue with another support, which is fixed contact. When you choose the fixed contact, first part is the slave part that needs to be assigned. It's the part of the structure where the mesh is not compatible, and the slave is always at the geometry that has smaller mesh size. So in our case, it's this middle part. And when we continue with pressing enter, automatically opens the assigning of master, and that is on the part of the structure where the mesh size is larger. So our structure is connected, it's supported, and now we can load it. So we go to load case prescribed deformation, and we prescribe it in epsilon direction, and the size is minus 0.1 millimeters. And at the top beam, at his bottom edge, we assign this prescribed deformation. And then we go to monitors because we need to see the results of our analysis. We need to be able to read it. So we are going to monitor reactions and displacement. So first we start this reaction on the surface. The reaction is in y direction again, and we are getting summation of all the nodal data. Then we continue with displacement monitor. It's always good to rename the monitor so you can easily find it in the postprocessor. Again, we are monitoring in a y direction, and for the displacement monitor, we choose the average. The last thing is that we can, I just wanted to show in this case that we can monitor also the reaction on the line where is the prescribed deformation, and it will give you the same result, basically like the reaction at the bottom where the structure is supported. So the displacement and the reaction monitor can be assigned to the same line. Then there are the solution parameters. We keep the default ones that are there. And then we go to the task where we describe loading history. In this example, we have simply one interval with all the load cases. And we are going to change the interval multiplier to 30 and divide it to 200 steps, and we save only every 10 steps to save the memory. Then we add the support load case and prescribed deformation. With interval multiplier 30, we are getting the total deformation 3 millimeters in this case, and we save it. And then we have to press on the task in the table, and then we can start to run the analysis. Pressing run automatically starts analysis in ATENA Studio. That is part of ATENA software for runtime and for post-processing of the results. And during the runtime, it's possible to see the LD diagram or other diagrams that you can define through your monitors that you defined in the preprocessor. In our case, we defined 3 monitors in preprocessing. One was for the deformation, and then 2 for reactions. And in this case, I'm creating the LD diagram for reaction that is at the support. You can also see how the structure is deforming, and you can also visualize cracks that are developing in the structure, which is like right below the deformation. And here we can do the second LD diagram with the same deformation, but the reaction was collected on the line where we prescribed deformation, and it should give you the same results like the previous one. Here are the cracks. We can show just the first level of cracks, which are like first direction where the crack appears in the element. Then we can check that the LD diagrams are developing the same way. The green progress bar shows you how fast it is running. When you go to the top right corner to press the icon next to Postprocessor, you can see that the drawing of results is hidden, and because of that the analysis can run much faster, which can save some time, of course, especially if you have some larger structures. And when you open it again, you can again check how the drawing of results is developing. And beside the deformation and cracks, you can also see some scalar results, which might be quite helpful. Here you can set, for example, crack width and apply it, and it shows you the color scale of the crack width within the whole structure. Once the analysis is completed, you can switch the runtime to post-processing, and it switches into mode where you can check results in different steps. So you can switch in between the steps that were saved. And you can also go to change the view from 3D or all elements to 1D elements to see, like, for example, stresses in bars. And actually this is extremely brief view into post-processing in ATENA Studio, and you actually can check the webinar that is dedicated to post-processing and deeper view. It is called Overview and Advanced Topics on Post-Processing and Nonlinear Analysis Evaluation in ATENA. You can find it on YouTube.
ATENA program produced by Chervenka company. You can find us via the website and download the program from it, or on YouTube by name Chervenka Consulting, or in Facebook by name ATENA. Finally, we thank you for your attention, and for any inquiries, please don't hesitate to contact us. Have a nice day. Bye bye.